Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to waves and oscillations, and we will take our discussion forward related to simple harmonic motion. In the previous videos we discussed about some important parameters related to simple harmonic motion, about the basic dynamics of simple harmonic motion, and then the energy of an object undergoing simple harmonic motion, the kinetic energy, potential energy, the total energy, everything. So in this video we are going to discuss, analyze some examples of simple harmonic motion and how the example, we know that this motion of the object, this particular example is actually simple harmonic motion, SHM. So let's get started. So this is oscillations of a loaded spring, okay. So that basic, which is popularly used in an analysis of simple harmonic motion. So as we know, simple harmonic motion basically involves oscillatory movement of an object around the two extreme points and from one extreme to another, and the important position is the starting position, the equilibrium or mean position, and the displacement versus time graph is basically a sine or cosine graph, where we have discussed all the important parameters: amplitude, time period, frequency, everything. So here we'll try to understand it with the help of a loaded spring arrangement. So here we have a block of mass m, and it is attached to one end of a horizontal spring, while the other end is connected to a fixed rigid support. This is the initial position of the spring, okay. It is at rest, but it is free to move over a, let's say if it is kept on a smooth frictionless surface, horizontal surface. So here from this position it can undergo expansion or it can undergo compression. Now whenever it undergoes displacement, let's say it undergoes displacement by a factor, let's say x, to the right. In that case, the spring, it exerts a restoring force in the opposite direction. We have already discussed about that the restoring force always tries to bring the mass towards the equilibrium position. That's why it is always in the opposite direction to the displacement, the direction in which the block of mass or the object is moving. So as per Hooke's law, the restoring force value is given by minus kx, where k is the spring constant and it is a value which is fixed for a particular spring. It is also called as force constant, and x is the particular displacement of the block from the mean or equilibrium position. Now this equation, the restoring force minus kx, this is the equation which is very important. Whenever you see this kind of an equation for a restoring force, you understand that that object will undergo or will exhibit simple harmonic motion, okay. And here the two important parameters which are there for the oscillatory movement are time period and frequency, okay, time period and frequency. So we have already derived the values for time period and frequency. So the time period t, it is generally expressed as 2 pi root over of the mass of the block divided by the spring constant, and the frequency is generally the reciprocal of time period, which is 1 by 2 pi root over of k by m. This is the general principle. And also in some cases it can also be expressed in terms of the instantaneous displacement and acceleration. So in that case it can also be expressed as 2 pi root over of x by a. Okay, the instantaneous displacement SHM we can also write. So please notice here that the general what we are using, the sign or symbol which we are using for instantaneous displacement, some cases we have used y, some cases we have used x, so don't confuse with that. Okay, so basically in essence what it means is that the displacement from the mean position, you can use x, you can use y, you can use z, you can use whatever, but the meaning remains the same. Okay, so here it is this, or we can simply write this as 2 pi instantaneous displacement from mean position divided by acceleration, that. So this instantaneous displacement can be represented by y, x, you can write y subscript SHM, you can write x subscript SHM, you can write whatever you like. Similarly, frequency will be simply the reciprocal of the time period, which will be 1 by 2 pi root over of a by x, or a stands for acceleration, x stands for instantaneous displacement. That you can also represent it in this way. So whatever you like. So this is for a horizontal spring. Situation totally changes when we have a vertical spring, because in that case when we attach a mass here, gravity comes into play, acceleration due to gravity comes into play, and things change. So in that case what will happen is that in the initial position, okay, in the initial position here, the spring is here with the spring constant, let's say we have spring constant k. Here there is no mass attached to it. One end is connected to the rigid support, the other end is free. In this condition it is neither compressed or stretched. Suppose we connect a mass to one end. In that case what happens, the spring undergoes displacement from the reference position or the equilibrium position, okay, from this point. From this point it undergoes displacement. Let's say it undergoes displacement by L. So in that case a restoring force will act. It is represented here by F1. Now this restoring force is always in the opposite direction to the displacement and is always given by this, proportional to the displacement, instantaneous displacement, and in the opposite direction by the minus sign. K is the spring constant. The weight of the mass because of acceleration due to gravity, that is mg, it is acting downward, F1 is upward. Now the net force, okay, this is upward, this is downward. The net force acting on the system in equilibrium, which is the final equilibrium position here, that is given by minus KL plus mg, which is equal to 0, because the net force acting on it is 0. Only then we can call it the equilibrium position. That is the case. Then from this equilibrium position, if it undergoes further displacement from this equilibrium position, if it undergoes further displacement, let's say by a factor of y, in that case the total displacement from the equilibrium position, the total displacement from this equilibrium position is L plus y. Okay, in that case the restoring force is F2, again in the opposite direction, and again it is directly proportional to the total displacement, in this case L plus y minus sign because of opposite direction. Again gravity, the weight acting downward, so the net force again is 0 because it is in equilibrium position. The next equilibrium position, it is stable in this position, So the total force acting on it is minus KL plus Y plus mg. Okay, this is upward, mg is downward, so it is 0. Okay, KL plus mg is this is 0. Sorry, the net force we have to calculate. Okay, so here if we try to expand it, it will become minus KL minus KY plus mg. This here we have calculated that minus KL plus mg is equal to 0 because it was the equilibrium position. Here if we substitute that, okay, F net is equal to minus KL plus mg minus ky. This much portion, it is 0. So only we are left with F net is equal to minus ky. This. So this is the net force. So don't get confused here. First, the spring was in this initial position with no mass attached, spring constant K. When we attached a mass, let's say of mass m, it undergoes some amount of displacement from this equilibrium position, let's call it L. Because of that, a restoring force F1 acts in the upward direction opposite to the downward displacement and is given by minus KL. Here this was the equilibrium position, stable position. That's why the total force acting on it is 0, net force is 0. In that case it is minus KL plus mg is equal to 0. Next, from this position, if it is further displaced by a factor y, still from this position, again little bit displacement by a factor y. In that case the net displacement is L plus y. Again there will be another restoring force acting upward, that is given by minus K L plus y. Mg is acting downward. In this case the total force is minus KL plus y plus mg. KL plus mg, this is we calculated as 0, and minus KL plus mg, we substituted that and we got the net force acting on it is minus Ky. Okay, and this is the whole thing. Again here also, if we want to determine the time period and frequency, it will also be in the same way. So if we use Newton's second law, we know that force is equal to mass into acceleration. So we can equate mass into acceleration is equal to minus ky. So acceleration is equal to minus k by my. And if we want to determine the time period and frequency, we can do it in this way by putting the acceleration value, time period is equal to instantaneous displacement by acceleration, or we can also do it in this way. Okay, mass and spring constant, the same thing. Okay, the same equations are valid. So here we have discussed about the example of simple harmonic motion, loaded spring, first in the horizontal position, next in the vertical position. So in the vertical position, because of the influence of gravity, there are a little bit of difference between horizontal movement of loaded spring and vertical movement of a loaded spring. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.